So good morning all. Today we will discuss the concept of mixing. Okay. So before we start with what is modulation and what is the need for modulation, this process of mixing is an essential concept that you should understand. Okay. So we will study in detail the concept of linear mixing, or it is also called linear summing. The other one is called non-linear mixing. Okay. So we will study two types of mixing. One is called linear mixing and non-linear mixing. And why should we study this mixing? The reason is in any communication system, you will have mixing of signals. That is, you will have a carrier signal and a message signal. So definitely you should know how to mix the signals. Okay, so that is why mixing is an essential concept in a communication system. Okay, mixing simply means process of combining one or more signals. Okay, so that is called mixing. And here I said we will discuss linear mixing and non-linear mixing. Also, in linear mixing and non-linear mixing, we will study based on two inputs. Okay, so linear mixing we will study based on single input and multiple input, and whereas in non-linear mixing also we will study based on single input and multiple input. Okay, so that is how we are going to analyze this mixing concept. Okay, so here you could see linear amplifier with a gain A. Okay, so Vin is nothing but your input signal. Vin is nothing but your input voltage signal. Okay, and V output is your output signal. And you know linear amplifier. So a linear amplifier, the output is gain times your input. So you know this, correct? So for an amplifier, the output is gain times your input. So V out is nothing but A times Vs. Okay, A times your input Vs. And here you could see the time domain representation and frequency domain representation. Okay, so this is your time domain representation. See, this is a sign we are going to analyze with help of a sinusoidal input signal. We are going to take a sinusoidal input is given as an input Vin to a linear amplifier. We are going to study the output. Okay, so my input signal is nothing but a sinusoidal signal with a definite frequency FA. Okay, so FA is my input frequency of my sinusoidal signal, and its amplitude is nothing but Vin. Okay, so the peak to peak amplitude here is Vin, and the frequency of this sinusoidal signal is FA. Okay, and this is at your input side. Okay, at your output side, you could see V out is equal to A times Vs. Correct. So what is this A times Vs? A times Vs is nothing but gain times your input. So your input is amplified by a factor A. Okay. So see, you could see the output. You have an amplified output because it is at the output of your amplifier. Okay. And we will see this frequency domain representation later. Okay. So here you are giving only one input. See, this is a single input frequency, and your frequency is FA. Okay, and your amplitude is BA. BA sine 2 pi FAT is nothing but a sinusoidal signal mathematical representation. So Vin is nothing but VA sine 2 pi FA into T is your sinusoidal input signal. So you know that output is A times your input. So A into VA sine 2 pi FA T. Okay, so this is nothing but your time domain analysis. So the difference between your time domain in input and output is amplified by a factor A. That is the only difference. Okay, and see, you see the figure. This is a sinusoidal signal. I hope we have learned this in signals and systems that if you take Fourier transform of a sinusoidal signal, you will have what? An impulse spaced at the frequency of your sinusoidal signal. For example, if you see here, your input frequency is FA. So if you take Fourier transform of the signal, you will have your impulse spaced at what? At frequency FA. So that is what? So if you take Fourier transform representation of a sinusoidal signal, you will have impulse spaced at the corresponding frequency. So here you will have your impulse spaced at frequency FA. Okay. So what is your voltage at FA? VA is your voltage. Okay, this is at your input side. The frequency domain representation is nothing but you will have a peak. We have done this in signals and system as well as in DSP. So if you take Fourier transform representation of a sinusoidal signal, you will have a peak at the corresponding frequency. So you have a frequency peak at FA. Okay, and similarly in the output, if you see the output V out also, the frequency is at FA. So the frequency is not altered here. Okay, so the frequency is not altered, the frequency remains same for both your input as well as your output. For V in and V out also, the frequency FA remains same. But however, the output alone, the output voltage alone is varying. For your input side, your output voltage is VA, whereas your output side, your output voltage is gain times your VA. So that is what this figure. So at frequency FA, you have VA, and at frequency FA, in your output side, you have gain times your voltage. Okay, so that is what. So this is nothing but linear mixing at your input side with a single frequency. Okay, and here so there is something called linear device and a non-linear device. If your output follows linear variation of your input, it is called linear device. See, output is A times your input. A is your factor, gain factor. So this is nothing but a linear device. So small signal amplifiers and passive networks are all examples for linear amplifiers. Okay, so a small signal amplifier is capable of performing linear amplification process. So we will use small signal amplifier for this linear amplification process. Okay. And here the main observation from our discussion, see, for single input frequency, you could see that both the input and the output have frequency content at your frequency FA. There is no addition of new frequency component. Okay. Whatever is your input, in the output also you have the same input, but magnified by 8 times. How about your frequency? In the input also it is FA, in the output also it is FA. See, in the input side also your frequency component is FA. The output side also your frequency component is FA. So no frequency component is added. The input frequency component is preserved at your output frequency component. Okay, so this is called linear mixing with a single input. The same condition we are going to analyze for linear mixing with the multiple input. So we are going to analyze what will happen if your input is more than one. So that is what your next discussion. Okay, so see here, linear mixing with two inputs. So we have a linear amplifier, okay, but here input is two inputs. So you will have two signals, that is with frequency FA and with frequency FB, with voltage VA and with voltage VB. So you will have first signal with voltage VA and frequency FA. The second signal will have voltage VB with frequency FB. Okay, and this is given to a linear amplifier, and the linear amplifier, the output is given as gain. See, there are two inputs, so we are just summing it up. It is also called linear mixing or linear summing. So we are just adding your inputs. So A times your input, what? BA. BA is what? Your input amplitude for one input, and BB is what? Input amplitude for second input. So your output is what? A times VA plus A times VB. Okay, so, and we have learned this as well. When you have a composite signal, what is the Fourier transform of a composite signal? For example, A cos 2 pi FAT plus B cos 2 pi FBT. So if we take Fourier transform, you will have two peaks, one at FA and another at FB. So that is what we have learned this also in signals and systems. When you take a composite signal and you take frequency spectrum, you will have your signal at both the frequencies, FA as well as FB. So that is what we are going to analyze. So here your input is at FA and FB, the output is at FA plus FB. So you will have both the components, one at FA and another at FB. Okay. So see, time domain representation. So this is your input voltage VA and this is your input voltage VB. So now both are summed by A times. So A into VA plus VB. So when you add this signal VA and signal VB, you will have a signal like this. Okay, this is nothing but linear sum of two sinusoidal signals. This output waveform, your third one, whatever I'm showing here, V out is nothing but linear sum of your input VA and input VB. So you will have a curve like this. Okay, this is addition of two signals. If you plot the sinusoidal waveform of two sinusoidal signals added up, you will have a signal like this. Okay, and see, in your input side, you have what? This is your output. AVA plus AVB is your time domain representation output. Okay, and at your input side, you have two inputs. Okay, so it is VA plus VB. So what will be your frequency component? FA and FB. So at FA, your input is VA, and at FB, your input is VB. See, we are just adding two signals here. Okay, in your previous circuit, linear mixing with one input, so there is only one input. But here we are adding two inputs. Okay, so since you are adding two inputs, you will have two peaks. If it is a composite signal, definitely in frequency domain representation, we know that we will have two peaks. So you have a peak at FA with amplitude dA, and you have a peak at FB with amplitude dB. Okay, so that is what your frequency domain representation at your input side. Okay, and now at your output side, it is similar to your input side, except the factor, it is amplified by a gain factor A. Okay, so the frequency component will remain same, FA and FB, but your amplitude alone is amplified by a factor A. Okay, so you have ABA and ABB. Okay, so that is how your frequency domain representation for this particular linear mixing with two inputs. See, very simple. It is also called linear summing. That is, you are adding two signals and you are giving it to an amplifier. That's all. Okay. Just like A cos 2 pi FAT plus B cos 2 pi FBT. You are adding two signals. That additive sum you are giving to a linear amplifier. That is what linear mixing with two inputs. And here the analysis is simpler. V out is A times V in. You know, V in is what? Addition of two signals. VA sine 2 pi FAT plus VB sine 2 pi FBT. Okay, and V out is what? Gain times your input. VA sine 2 pi FAT plus VB sine 2 pi FBT. Okay, so here also our analysis is both input and output, both V in and V out is having frequencies at FA and FB. See, if you see the representation, you have your components at FA and FB. So that is what my analysis. So in linear mixing, if I want to sum it up, this is what I understood from the discussion is, in linear summing occurs when two or more signals combines in a linear device. Linear device means what? The output and input follows a linear relation. That is called linear device. So that is one thing. So linear summing, that is two signals will get added up when two or more signals combine to a linear device. That is our one important observation. And both the cases, single input and multiple input, we have observed that signals combine in such a way that no new frequency components are produced. See, if your input is FA, your output is also at FA. If your input is at FA and FB, your output is also at FA and FB. So no new frequency component are introduced. The input frequency component and output frequency component remain as such. Okay, there is no addition of new frequency component. Okay, so definitely this linear mixing is not used in modulation process. However, this linear mixing, the spectrum is preserved. Whatever is your input spectrum, the output spectrum is preserved except with an addition of an amplification factor A. Okay. So whenever you require applications which demand preserving of your spectrum, you go for linear mixing. Okay. So it is normally used in high fidelity audio applications. So that is what linear mixing is all about. Okay. Thank you.